For our final project, we implemented the paper Point2Mesh, a self-prior for deformable meshes. This paper aims to reconstruct 3D meshes from point clouds using mesh-based convolutional neural networks. Mesh-based CNNs assign each edge a feature and support convolution, pooling, and unpooling. Convolution kernels are defined over neighborhoods of 5 edges. Pooling is based on the edge collapse operation, where an edge shrinks until it becomes a vertex, while unpooling reverses pooling using a memory of previous mesh states.
The authors start by fitting a convex hull to the input point cloud. They then assign fixed random features to the edges and fit this through a mesh-based CNN. The output features are interpreted as edge displacements, which are averaged to produce vertex displacements. These displacements are optimized for 1,000 iterations. Then the mesh is subdivided, and the process repeats. The network uses 2 losses, a chamfer distance loss and a beam gap loss. The chamfer distance loss aims to minimize the distance between sample surface points and nearby point cloud points. The beam gap loss, which helps the mesh enter deep cavities, aims to minimize the distance from each face's centroid to the nearest point cloud point within a narrow double cone.
Overall, we were able to reproduce many of the paper's results. However, we found that the beam gap loss often produces noisy meshes, and the pooling has little effect on the final output. We also found that some meshes converge faster than others, so our implementation cuts off training once it detects convergence.